Hello, dear colleagues. Welcome back to Physics 161 recitation session. Today we are discussing momentum, impulse, and the way how to solve the problems with these new concepts of the problems of the physics. So let me change my camera. So the first problem is as follows. Two blocks of masses m and 3m are placed on a frictionless horizontal surface. A light spring is attached to the more massive block, and the blocks are pushed together with the spring between them. A cord initially holding the blocks together is burned. After that happens, the block of mass 3m moves to the right with a speed of 2 meters per second. First question, what is the velocity of the block of mass m? And B, find the system's original elastic potential energy taking m equals 0.35 kilograms. So first, let's draw what is given in the problem. Let's draw this drawing again, and then we will collect all the given information. So we have that there are two blocks. So first block, small one, has a mass of m. And there is a spring which is compressed, and they interact through this compressed spring, while the spring is connected to the block with the bigger mass 3m. And they're connected with the cord, and this cord holds them together. The surface is frictionless, so there is no friction, there is no energy loss in the form of the change of the internal energy. So after this cord is burned, the following is happening here. So we have this small block and we have this bigger block. Now the spring is not compressed, it is decompressed, it's free. And this guy with a mass 3m moves to the right with a velocity v2 final. And this guy is moving to the left with a velocity of v1 final. So we need to find the velocity of this first object because this velocity is given. So first, let's collect what is given in a given box. So the mass of the first block is m small, mass of the second block is 3m. So there is no friction, so coefficient of friction is 0. And the final speed after the cord is burned of this massive object is 2 meters per second. Okay, we need to find first the speed of the first object, this m, when the cord is burned, and b. Now, if the m is given, which is here and here, it's 0.35 kilograms. So we need to find the system's original elastic potential energy. So potential energy is question. So before we start solving this problem, let me briefly remind you that according to Newton's second law, if there is some external force acting on the system, let's call it F net, the system or the object will move with some acceleration. But acceleration, so net or external, is a change of velocity, dv dt. So with respect to time, mass is a constant, so we can place this m to this part. So that will give us dmv dt. Okay, and if we introduce a new parameter called momentum, which is equal to mv, then the force which is introduced into the system will lead to the change of a momentum with respect to time. Okay, that's just to remind you a concept of the momentum, like that. So if you look at this equation, if there is no any external object acting on the system, or there is no net force, so if net force is 0, so then the change of momentum would be equal to 0. So if it is 0, dp dt is 0, which means that momentum is constant during the entire process, or delta p is constant, if you wish to say it like that. So this case, when there is no any external agents that are acting on the system, we say that the system is isolated. Okay. So from this statement, we can say that before the interaction, which is P initial, and after the interaction, which is P final, the momentum of the system is conserved. Now let's look at this problem. So let's assume that the system consists of two objects in this spring. So in that case, there is no any, and also gravitational field. So in that case, we can say that there is no any external agent acting on the system. So which means that the system is isolated. So if so, then the momentum of the system should be conserved. So dp delta p equals to constant, or initial momentum of the total system equals to the final momentum of the total system. So now let's look what is happening at the beginning. So before the core is burned, before and after the core is burned after. So what was the initial momentum of the system? So since nothing is moving here, so this is definition of momentum. So mv1 initial time plus mv2 v2 initial, it's 0 because they are not moving. So initial momentum is 0, but final momentum is not 0 because they're now moving. So the total momentum of the system equals to, so this is final momentum, equals to object m1 v1 final. So we can skip this vector notation because everything is happening is on along one axis. So this is just like that, coordinate system like that. So everything is happening along x-axis. So that would be just m1 v1 final. So this is momentum of the first object plus momentum of the second object, v2 final. So in our case, so we can see that this is 0 equals to this guy. And in our case, the mass of the small object is just m times v1 final plus the mass of the second object is 3m times v2 final. So we can cancel the masses here, and from that you can obtain, and we need to find this v1 final, the speed of the small object after the core is burned. So we can now express and find this v1 final. That would be equal to 3 times minus v final. So this is minus 6 meters per second. So it will move in opposite direction with respect to the motion of the bigger guy. So here is the answer for the first part of the problem. Now we need to find the elastic potential energy stored in the system at the beginning. So since there is no friction in the system, we can say that total mechanical energy of the system is conserved. Agree? So there is no any change of the internal energy. So if so, at the beginning, the only energy here in the system is stored in the spring, and after that, spring is released, but there are two objects moving with different velocities and different speeds, which means that this initial potential energy stored in the spring equals to the total kinetic energy after the spring is released. Agree? So that's why we can say that U initial equals to K final. And just let's calculate the final kinetic energy. That would be just 1 over 2m, the mass of the small object, times v1 final squared that we just found, plus 1 over 2, the mass of the second object, which is 3m, times v2 final squared, which is given in the problem. So when you substitute the given information about m, it's 0.25, it is given in the problem. You can find that Q, which is elastic potential energy stored in the system before the core is burned, equal to this guy, v1 final squared plus 3 times v2 final squared. Numerical value would be 8.4 joules. So that's the answer for the part B of the problem. So questions, please. Okay, no questions. Let's then solve the next problem. Now let's work with the concept of impulse. So the problem is as follows. The magnitude of the net force exerted in the x direction on 2.5 kilogram particle varies in time as shown in this figure. Find A, the impulse of the force over the 5 seconds time interval. B, the final velocity the particle attains if it is originally at rest. C, its final velocity if its original velocity is minus 2 I hat meters per second. So this is unit vector with respect to x-axis. And D, the average force exerted on the particle for the time interval between 0 and 5 seconds. Okay, so first let me draw this function. So the force as a function of time. And then we will discuss this concept of impulse. So now we have, that would be a solution box, solution. So we have the force as a function of time. So it's time in seconds. This is a force in newtons. So here we have 1, 2, 3, 4, 5 seconds. This is 5, this is 0, 1, 2, 3, 4. And the absolute values at some moment of time are 1, 2, 3, 4 newtons. So first 2 seconds, the force increases linearly from 0 to 4 newtons. It's given in the problem. Then the force applied to the system remains the same during the next 1 second, and then it goes down again linearly in the next 2 seconds. So from 4 newtons to 0 in 5 seconds. So that is given in the problem. That is a function of force with respect to time. And it is given that this force is applied to the particle with a mass of 2.5 kilograms. And we need to find the impulse. B, we need to find if the initial speed of the particle is 0, we need to find the final speed of the particle after it was affected by this force in 5 seconds. So C, if the initial velocity of the object of the particle is minus 2I hat meters per second, what will be the final velocity after the impact of this force? And D, we need to find the average force between the moments of time t1 equals 0 and t2 equals 5 seconds. So F average we need to find. Okay. So let me now briefly remind you the concept of the impulse. So in previous problem, we already discussed that. So let's skip the vector notation. If there is the action of the external force on the system, it will lead to the change of a momentum. So this is equal to mv. So we can move this m from the differentiation operation, and that will be just ma. So the change of momentum is caused by the external force. Now system is not isolated. There is some external agent acting on the particle or on the object. So from that, we can say that the small change of the momentum just from this equation equals to external force times dt. And if you need to find the total change of the momentum of the system, if now the force is a function of time, we just need to integrate this force from the moment of time to t1 and to this moment of time t2, and you will find the change of momentum between these two moments of time. So this is this is equal to momentum. So this change of the this is called impulse, and impulse is equal to the change of momentum, and it is also equal to the integral of f dt. So this is a definition. So when you look at this expression, you can notice that if you have a force as a function of time in graphical representation like that, so this impulse would be equal to the area under the line, which represents the force as a function of time. So if you need to find this impulse from the moment of time 0 and 5, you just need to find the area of this entire figure. So in our particular case, the force is given not as a function, but as a graph. But this graph is relatively simple. So we just need now to find the area of this figure. Okay. So this figure consists of 3 parts. This is the first part. This is right triangle. So this is a rectangle here. And the third part, again, right triangle. So it's easy to find that the total area of this figure equals to, so now relative to our problem. T1, T2, F dt. So area equals to, so look at the length of this side of triangle, look at the length through the graph, look at the length of this side of triangle, this is equal to 4, and then multiply them and take 1/2, 1/2, that would be the area of the triangle. So that would be 1/2 times 2 times 4 plus the area of this rectangle, just 1, this length times 4, this length. So this is plus 1 times 4 and plus again 1/2, the same size of this side, the same size of this side, but let's use it like that. So it's 1/2 times 2 times 4. So just find this expression, and it is equal to 12 newtons times seconds. So that is a momentum in our problem, or the change, excuse me, not momentum, but impulse. So that's the impulse in our problem. So from the moment of time t equals 0 and 5 seconds, the momentum is changed by this value of the impulse. It's 12 newtons times second. Okay, now we need to find, if the initial speed of the particle was 0, we need to find the final speed. So how to do that? So we found this one impulse, it's here, and it is also equal to the change of the momentum. So if so, let's just find the change of the momentum, which is equal to the delta p equals to momentum final minus momentum initial, and that would be equal again from the definition of momentum to the m times v final minus m times v initial. So from definition of momentum, and we found this delta p, it is equal to I. So impulse equals to this guy, mv final minus mv initial. And from here, v initial is 0, it is given in the problem. We can easily find v final. So in general, v final will be impulse minus, plus mv initial over m. So now substitute v equals 0 at the beginning, momentum we just found here. Mass is the given in the problem, it's 2.5 kilograms. And in the part B of the problem, the final speed of the particle would be equal to 4.8 meters per second. Okay, now in the part C, we have to find the final velocity if the initial velocity is minus 2 I hat meters per second. We need to find the final velocity. So again, just use this expression, general expression. It can be also expressed in a vectors form. And you will just substitute this initial here, since this is one-dimensional motion. So just v final vector equals to momentum plus m v initial over m. So just first find the absolute value and multiply by this I. So the absolute value would be 2.8 meters per second. So the vector would be 2.8 times I hat. So it will move in opposite direction, and the speed will be increased with respect to initial speed. So next part, we need to find the average force. Now let me briefly remind you a concept of the average force. So in general, we said that force can be not constant. The force which is acting on the object can be a function of time. It may be not constant. So it can behave like that as a function of time. And if you need to find the average speed, the concept of, average force. So the momentum, let's say from this moment of time to this moment of time, or here, let's say from the moment of time t1 and the moment of time t2. So the momentum between, not momentum, but impulse between these two parts equals to the area under this line. That would be the change of momentum, and that would be equal to the impulse from this definition. Okay, but the average force is just some constant force, so some value of constant force, F average, which will give you the same area when multiplied by this period of time. Okay, so that's the idea of the average force. Now, in our problem, we need to find the average force from t equals 0 to 5 seconds, so the entire period of the force action. And we already found the area under this line. Momentum, it's here, 12. And now to find the average force average can be just equal to the impulse divided by delta t. Delta t is just 5 seconds. So the numerical value will be just 12 over 5 seconds, and that's equal to 2.4 newtons. So the constant force with a magnitude of 2.4 newtons, which is acting on the object in 5 seconds, would lead to the same change of a momentum, and it would have the same impulse in the process. Okay, so this magnitude. So questions, please. So this is the answer for part.
I have a question.
Yes, please.
In point C, did you substitute -2 for I initial?
Excuse me?
In part C,
Yes.
did you substitute -2?
Yes, it was -2.
Ah, okay, thank you.
This is 12 plus -2 times 2.5. Mass is 2.5. This is -2. I substituted -2. So that is 7 over 2.5. The answer is 2.8. So let me write it here. So that is 12 minus numerical value just of this expression. 12 minus 2.5 times 2. So this is -2 over 2.5. This is a mass, this is a speed. Okay, so thank you for questions. Please, more questions? No? Then let's solve the next problem. Now let's consider a collision of two objects. So the problem is as follows. 1,200 kilograms car traveling initially at V car initial speed 25 meters per second in an easterly direction crashes into the back of 9,000 kilogram truck moving in the same direction at this speed 20 meters per second. The velocity of the car immediately after the collision is 18 meters per second to the east, so the same direction as it was at the beginning. A, what is the velocity of the truck immediately after the collision? And B, what is the change in mechanical energy of the car track system in the collision? So, okay, let's first collect what is given. Excuse me. So, the given box. So the mass of the car is 1,200 kilogram. Its initial speed is 25 meters per second. So they are moving along a straight line to the east. So the mass of the track is 9,000 kilograms. The speed, the final speed of the car is 18 meters per second. So in the same direction. So it was 25 at the beginning, and after the collision, it has the speed of 18 meters per second. So we need to find what is the final speed of the track after the interaction. V of the track final after the interaction. And B, we need to find the change of mechanical energy of the car track system. Okay, so now let's solve this problem. Solution. So let's again just briefly draw what is happening in general. So here is a car, here is a track. This guy is moving to some V initial. So it's V initial, VC initial. This guy is moving with the speed V track initial in this direction. So this crashes to this guy, and after the interaction, they have different speeds with respect to initial. So this guy has V track final speed, and this guy has V car final speed. So that was before the interaction, before the collision. This is after collision, after. So with respect to the system, we can say that there is no any external force acting on the system, which means that F external is 0. So if so, there is no change of the impulse of this of the momentum of the system. The change is 0. And from this statement, initial momentum equals to the final momentum of the entire system. Now let's just look through the problem. So what was in general, what was the initial momentum of the entire system? So that was the mass of the car times speed of the car initial plus mass of the track times speed track initial. That was before the collision. And after the collision, mass of the car times final speed of the car plus mass of the track times V track final. And as I said, as I already mentioned, there is no any external force, which means that the momentum of the system is conserved. So they're equal to each other. So from that equation, now you can easily find the final speed of the track because all the rest parameters are given in the problem. So from that, just general form, V track final equals to M car V car initial plus mass of the track V of the track initial minus mass of the car times speed of the car initial divided by mass of the track. Substitute all the given numbers and you will obtain that the final speed of the track is 20.9 meters per second. Okay, so this is solution for the first part of the problem. Now let's discuss the change of the mechanical energy of the system. So in general here, mechanical energy means that kinetic energy plus potential energy, elastic potential energy and gravitational potential energy. In general, there is no any change of potential or gravitational potential energy. Also, nothing is compressed, so there is no any spring which can release the energy. So which means that the only change of the total energy of the system is just the change of the kinetic energy of the system before and after collision. So if so, let's just again write this statement. So in general, the change of mechanical energy of the system equals to the change of the kinetic energy plus the change of potential energy. So in our case, this guy is 0. They are the same height. There is no spring. So that's why the change of the total mechanical energy equals to the change of the kinetic energy. So just calculate K final total minus K initial total. That will give you the change of the total mechanical energy of the system. So if you continue the solution here, so delta E equals, so just to keep it on the video, it's 1/2 M car final times V car final squared. So this is the final kinetic energy of the car plus final kinetic energy of the track, V track final squared. So minus initial kinetic energy of the entire system. So this is 1/2 MC VC initial squared plus 1/2 mass of the track times V track initial squared. Okay, so substitute all the numbers here. Now everything is done. We found the previous part here. All the rest is given. And you will obtain that the change of the mechanical energy equals to the minus 8.7 times 10⁻³ joules. So which means that now kinetic energy is decreased. The kinetic energy decreased, but the total energy of the system obviously is conserved. We just lost some part of the kinetic energy and it was transferred to the internal energy of the system. And that's the idea also of the momentum. Even when the mechanical energy is not conserved, which means that it is not easy to calculate all the needed information, but the momentum of the system is always conserved for the isolated system. Okay? So that's the idea of this problem. So questions, please.
No questions.
Okay, thank you. So now let's solve the next problem. In the next problem, we will analyze a collision not along a straight line, but in 2 dimensions. So the problem is as follows. A billiard ball moving at 5 meters per second strikes a stationary ball of the same mass. After the collision, the first ball moves at 4.33 meters per second at an angle of 30 degrees with respect to the original line of motion. Assuming an elastic collision and ignoring friction and rotational motion, find the struck ball's velocity after the collision. Okay, so let's again draw some sketch at the beginning in order to understand what is happening. So let's draw it here. So initially, the second ball was at rest. So initial speed of the second ball is 0. And there is a line of interaction. And the initial speed of the first ball was v1 initial, and it is given. So v1 initial given, v1 initial absolute value is 5 meters per second. And initially the speed of the second ball is 0. It was at rest. So after they interact with each other, so this is the line of interaction. After the interaction, they move at some not x, at some different lines, not with respect to the initial line of the interaction. So the first ball is moving here with some v final speed, and this v final speed is given. Excuse me, it's v1 final. So this v1 final is given. Absolute value is 4.33 meters per second. And theta, the angle with respect to the initial line, is 30 degrees. So this theta is 30 degrees, this angle, 30 degrees. And the second ball is moving somewhere that we have to find. So this is the second ball, which moves with different final speed and has a different theta 2. And we need to find this theta 2 in the absolute value. Okay, and also we have an elastic collision. Elastic means there is no change of the mechanical energy. No change in kinetic energy. That's elastic collision. Nothing goes to internal energy. Okay, so we need to find. Okay, let's connect it to be. So we final absolute value, and this angle theta 2. This angle theta 2. Okay, again, let's analyze this problem. So there is no any external agents acting on the system, which means that the system is isolated with respect to these two processes, before and after interaction. Isolated, so which means that the momentum must be conserved. Momentum of the system before and after interaction. But momentum is a vector. Okay. So which means that with this momentum conservation principle for the isolated system, we can find these velocities. So the initial momentum, what is the initial momentum of the system? It's just the mass of the object M, of the object 1. It is given that if we introduce a coordinate system like that, x, y, so it's directed to the right. It's just v1 initial times I hat, agree? So this speed, this is absolute value, which is given in the problem. And momentum after the interaction, total momentum. Total momentum of the system equals to the momentum of the object number 1 plus final momentum of the object number 2. It's like that. And now, so just let's express this guy in the form of mv. That will give us m times v1 final x plus m v2 final x. This is x component of the final momentum plus m times v1 final y component plus m v2 final y component times j hat. This is a vector. Okay, and they are equal to each other before and after interaction, since the momentum is conserved. So if so, let's just say that they are equal to each other, and we will obtain this general expression that will be just m times v1 initial I hat equals to this guy. Let's write it again. So x component of this momentum plus x component of this momentum I hat plus m v1 final y plus m2 v2 final y times j hat. So from that, we can find, so this is initial momentum, this is the final momentum in vector form. So from here, we can say that I component final equals to the I component initial of the momentum. So from that, we can say that, so we can cancel masses because they have the same masses. So this guy equals to this guy. Okay, so V1 initial equals to V1 final X plus V2 final X. Okay. And the same here. So J component of the final momentum must be equal to the J component of the initial momentum. And the J component of the initial momentum is 0, which means that the 0 equals to V1 final Y plus V2 final Y. So from this second equation, we can say that the final Y component of the final speed of the second ball equals to minus V1 final Y from here. And from here, we can express X component of the velocity of the second ball after the collision. So V2 final X equals to V initial minus P1 final X. Okay. So let me briefly remind you that, so here we can calculate from the problem X component and Y component of V1 velocity, because it is given that absolute value is known and this angle is known. Just let's find the X component of this velocity and Y component, and then let's substitute them here. So just to remind you, so V1 final X equals to V1 final absolute value times cosine theta, which is 30 degrees, and V1 final Y equals to V1 final times sine theta. V1 final times sine theta. So let's substitute these values here, and you will find, so let's put 1, equation 2, you will find X component of final speed of the second ball. So from 1, V2 final X equals to 5. The speed was 5 at the beginning minus this X component of V1. So this is 4.23 absolute value times cosine 30 degrees. Okay. From the equation 2, we can say that X component of velocity of the second ball equals to minus 4.23 times sine theta, sine 30 degrees. Sine 30 degrees. So the absolute value here is 1.25 meters per second. So here it's minus 2.16 meters per second. So we found the components of the vector V2 final. And you can now find the absolute value of this vector. It's just square root of V1 V2 final X squared plus V2 final Y squared. There here, absolute value is 2.49 meters per second. And this angle theta 2. So we found the components Y and X. You can find this theta. So theta 2 equals to tangent reverse function V2 final Y component divided by V2 final X component that are here. This is minus 60 degrees. So counterclockwise with respect to initial direction of motion. So here are the answer. This guy and this guy. Questions, please? No questions. Thank you. Good. Let's move forward. Let's solve some problem with the explosion. And in this problem, I will show you how to easier solve the previous problem. So the problem is as follows. A rocket is fired vertically upward. A rocket is fired vertically upward. At the instant it reaches an altitude of 1000 meters and a speed of v initial 300 meters per second, it explodes into 3 fragments having equal mass. One fragment moves upward with a speed of 450 meters per second following the explosion. The second fragment has a speed of 240 meters per second and is moving east right after the explosion. What is the velocity of the third fragment immediately after the explosion? Okay, so let's draw at the beginning what is given to understand what is happening. So we have a rocket, let's say with a mass m capital. It's this guy is moving upward. It is given the problem with some initial velocity, and then there is some explosion, and we have now 3 fragments of the 3 pieces of the rocket. First piece, second piece, and third piece, and they have the same masses. So this guy is moving upward. It is given in the problem. This guy is moving to the right with some velocity, and we need to find this vector, a velocity of a third piece. Okay, so now let's collect what is given in the problem. Given. So it reaches the altitude of 1000 meters, but in general, we don't need this information. So initial speed of the rocket is 300 meters per second. It is directed upward. So they have the same masses. So let's say that each piece has a mass of m1, m2, m3, and it's equal to the mass over 3, obviously, if we introduce this mass of the rocket as m capital. So v1, the speed of the first piece is 450 meters per second, and it is directed to the right. Excuse me, directed upward. So also upward. So this guy. So v2 absolute value of this velocity is 240 meters per second, and it is directed to the right. It is given in the problem. So we need to find a velocity v3. So velocity of this third fragment of the rocket. So in this case, the explosion is a part of the system. So this is a release of the energy, which is the entire internal energy. So with respect to the ground, so this system does not affected by any external forces. Okay, which means that there is no change of the momentum. Agree? So this is the momentum equals 0. So before the explosion, after the explosion, momentum is the same. So this is P initial vector equals to P final vector. Momentum before and after explosion, they're equal. Now let's express these momentums in the form of the definition. So initial momentum was mv initial vector. It is equal to the momentum after the explosion. And this is the sum of all the momentums of each pieces of the rocket. So that will be equal to the m over 3 times v1 vector plus m over 3 times v2 vector plus mass of the third piece times third vector velocity. Now let's analyze what is vi. Let's introduce a coordinate system like that, x and y. Let's introduce unit vectors I hat and j hat like that. So in terms of I and j hat vectors, v initial was directed upward, and absolute value is given, so it's just 300 j. v1 vector. v1 vector of the first velocity of the first piece is also directed upward, and the absolute value is 300 meters per second. Excuse me, 450 is here. So that's why it's 450 times j hat. The velocity of the second piece is directed to the right. It is given in the problem. So absolute value is 240, and we need to multiply it by I hat. So that would be just 240 times I hat. And v3 is just v3. So let's combine them together in this equation. Also, we can cancel capital M here, multiply by 3 both parts of the equation, and then substitute these vectors into this equation. So you will obtain that 3 times 300j, this is the initial part, equals to this guy 450j plus this guy 240i plus vector v that we have, vector v3 that we have to find. So now it's simple, v3 vector equals to, and they go here, it's minus 240 I had plus 450 j hat. Agree? Meters per second. So that's the expression for the vector in unit vectors form. And if you need to find the absolute value, just use this component and this component. If you need the exact angle, again, just use the x and y projections of this velocity. Okay? So problem is solved. Questions, please? Okay, good, no questions. So we don't have a lot of time, so let's skip the problem with spring, let's solve this problem. A small block of mass m1, 0.5 kilograms, is released from rest at the top of a frictionless curve-shaped wedge of mass m2, 3 kilograms, which sits on a frictionless horizontal surface, as shown in the figure. So everything is frictionless here. When the block leaves the wedge, its velocity is measured to be 4 meters per second. So right here, when it just left the wedge, the speed is 4 meters per second to the right, as shown in the figure. So we need to find the velocity of the wedge after the block reaches the horizontal surface. We need to find this velocity, and we need to find the height of the wedge. So again, let me draw this figure here, just to make it easier to see what is happening. So we have a curve-shaped wedge like that. Surface is frictionless. The surface is also frictionless. So there is a block with mass m that sits m1, that sits on the top of the wedge. Nothing is moving here. And then this guy goes down. It leaves the wedge with the final velocity. It's here, v1 final. Here is the wedge. Oh, it's not the same as here. So here is a wedge, and obviously this wedge will move to the left. Yeah? Why? Obviously because of the momentum conservation principle. So v2 final, we need to find. So let's collect what is it's v1. It's given in the problem that this object is m1, index 1. So given, let me collect the given information. The mass of the first object here, it's 0.5 kilograms. The mass of the object 2, this wedge, is 3 kilograms. This is m2. And now the friction there is no friction in the problem. Everything is frictionless. So coefficient of friction is 0. And v1 final is directed to the right and has the magnitude of 4 meters per second. So this is object number 1. This is object number 2. So we need to find the speed of the second object, which is a wedge, and the height. So this guy has a height. So we have only masses and final speed of the object. And we know that initially they were at rest. And interesting question, how to find the height and the speed of this guy. Well, again, with respect, when we consider the system of the Earth, the wedge, and block M1, there is no any external force acting on the system. Okay, so there is no any external agent acting on the system, which means that system is isolated and the change of momentum is 0. The change of momentum means that final momentum equals to initial momentum. So here we can skip vector notations because everything is happening in x-axis direction if we introduce it like that. So if so, let's consider what is P initial momentum of the system. Well, in general, it's 0 because nothing is moving here. So this is P initial, so let me replace them. So before equals to P final. And what is final momentum? Well, this is just M1 times V1 final, this guy, plus the momentum of the wedge, M2 times V2 final. And from here, we can easily find now the final speed of the second object of the wedge. That is equal to minus M1 over M2 times V1 final. And the numerical value would be minus 0.67 meters per second. So this is the speed. So it's directed in opposite direction with respect to the motion of the object M1. Now we need to find, so that was A, B, we need to find the height of the wedge. So in general, we know that energy conservation principle is valid always. This is energy conservation principle. And this change of the total energy system equals to the work done by the external agent. So we don't have any external agents here. So it's equals to 0. There is no friction, it's 0, which means that total mechanical energy is conserved in this process. And it's like that. So what is the mechanical energy? There are kinetic energies and potential energies in the system. So initially, let's consider the change of the kinetic energies. So obviously, kinetic energy final is equal to, so kinetic energy final is 1 over 2 block M1, V1 final squared. This is final, 1 over 2 times V2 times V2 final squared that we just found here, minus initial kinetic energy of both objects. So they both had 0 kinetic energy at the beginning. And we need to find plus the change of potential energy. And then if you look at the problem, you see that initially this guy had some potential energy with respect to the surface. And exactly this energy stored in the system leads to the motion when this guy goes down to the ground. Okay, so now change of potential energy. So final potential energy is 0. So there is no any potential energy stored in the system. Minus M1GH. And it is equal to 0 because work done by the external agent is 0. There is in general no external force. So from that, we can now find this height. We can express it like that, 1 over 2 M1 V1 final squared plus 1 over 2 M2 V2 final squared over M1G. When you substitute all the numbers, so this number V2 final we just found here. This guy is given, masses are known. So the height of the wedge is 0.95 meters. Okay, problem is solved. So we have, so questions, please. Okay, no questions. So let me solve the last problem. I just would like to introduce the concept of a center of mass. So this problem is relatively short, but the concept is important. So the problem is as follows. A rod of length 30 centimeters has a linear density, mass per length given by. So the rod has a linear density. Let me select it right now. Lambda is now function of x because you can see it here equals to 50 plus 20x. So the mass is distributed non-uniformly in the length. It depends on the position of the part of the rod that you're considering. So mass per unit length is not constant. So it's given. So it is also given that the length is 30 centimeters of the rod, which is 0.3 meters. Let's convert everything to meters and to seconds. So we need to find the total mass of the rod. I need to find B. So what is the mass of the rod and how far from the x equals 0 and is its center of mass? So how far the center of mass from one end of the rod? So we need to find, so in general, that's x coordinate since it's a rod or the center of mass. So solution. So let me just briefly explain what is happening here. So here is a rod. We have a rod. It lies on x coordinate system. So it's not moving, just coordinate system. This is initial, let's introduce the origin here. That would be the length. This coordinate would be the length. And when you look at the object, small piece of the rod that has length of dx and it has dm mass, then this object has a linear density dm dx, and this linear density is equal to this guy. Okay, so it depends on the position x, but this is definition of linear density. So now let's find the mass, total mass of the object. So linear density, as I already said, in our case it's a function of the position, is equal to dm dx. It's here. And in our problem, it is equal to 50 plus 20x. So from that, you can find that dm is equal to 50 plus 20x times dx. Now you can find the total mass, because you know the length. How to find it? The total mass of the rod will be just integral of dm through the entire length of this rod. So it's from 0 to L, 50 plus 20x dx. Okay? So just find the integral, that will be 50x plus 10x squared. Then substitute the limits. L is 0.3 meters. This end is 0. And numerical value would be 15.9 kilograms. So this is the mass of the rod. And final part of the question, we need to find a center of mass coordinate. So let me briefly remind you, if you have some coordinate system like that, so you introduce a coordinate system and you have a system of several particles like this, like this, like this. Let's say this guy has a mass of m1, this guy has a mass of m2, this guy has a mass of m3. So we can introduce a center of mass of this system. And the system of mass, center of mass. We can introduce a center of mass of this system, and the center of mass would have some coordinate which we can find from the following definition. So x coordinate of the center of mass equals to m1 x1, so with respect to this origin, m1 times x1, it's here, plus m2 x2, so this is x2 multiplied by the mass, plus m3 times x3, so this is a coordinate x3, and divided by the total mass of the system. So there may be more particles in the system. That's the way how to find the x coordinate of the center of mass. So this is center of mass. So y component is almost the same. So that would be just m1 mi yi over the total mass of the system. Okay. So I goes from 0 to k. In this case, k equals to 3. This is the same. From 1 to k. So if you have if you have a system of several particles, but if you have, when you look at this, and if you have a rigid object, like here, solid object, it means that there is an infinite number of small particles. You can replace this guy with the integration process. Okay, so that would be, so now the coordinate of the center of mass of the rigid object is equal to the total mass of the rigid object. So in denominator, so it's 1 over m times the integral x dm. So in our case, there is no y component since this is a rod, but for the y position of the center of mass or not the rod, you can also find from that, but replace this x with y. So now this is a definition for the rigid object x according to the center of mass. Now how to solve this problem? Unusual function to integrate, but we already introduced that dm over dx equals to lambda, and we can now find what lambda is in terms of x. So again, let me remind you that L equals to dm dx. So from that, dm we can express through lambda times dx. Now just substitute here. So coordinate of the center of mass x would be 1 over m integral x times lambda dx. So x came from here, and this lambda dx came from dm. Now lambda is given in this form, just substitute it here. So that was just to remind you. It is equal to 1 over m integral from 0 to L. Now it's x times 50 plus 20x dx. So just integrate this function, then substitute these limits, and we found the mass. It's 15.9 kilograms. Just divided by this mass, and you'll find that the coordinate of the center of mass is 0.153 meters. It's almost at the middle, but still a little bit further from one end. Okay, so that's the idea of the center of mass. So problem is solved. Questions, please?
No questions.
Okay, good. Then thank you for your attention. Bye-bye.
Thank you. Goodbye.
Bye-bye.